My name is Leszek. We'll be today talking about something that probably all of you do, but really no one thought how it works. I mean the scheduling. Each of you is running a laptop which probably has between 4 to 8 cores, can be HT siblings as well. And it's probably running about 100, maybe even more services, processes, applications on that. And it works quite smoothly. They don't block each other, they work. The UI become responsive. That is the modern systems. So how does it work? And what it has to do with the clusters? Actually, quite a lot, actually. Maybe a little bit worse about me. I'm currently working for government in a company, Axis Apps, it's IT consultancy. One of the projects we are working on is heavily related to Kubernetes cluster. Who does use Kubernetes, just out of curiosity? All right, so quite a few people. And who does it use from the more DevOps side? Like setting up declarative things, just 1, 3 people. All right, that's quite good. So probably some of you, when you were running an image or setting up pod, sometimes it was pending, blocking, and you all think what was happening there. And you go describe the pod, and you see it's pending, waiting for scheduler, things like that. So I will try to describe what's exactly happening there. Before we start, we should start with what are we talking today? We'll be talking about taxonomy schedulers. We will focus primarily on the cluster schedulers in this taxonomy. However, we also need to talk a little bit about what's happening in operating systems. And there's also another branch of big data schedulers. There are a few differences, but maybe not on this presentation. This is really a lot of material to cover. So let's start. Let's start with operating systems. All of it started with DOS, which was first truly a multitasking system. When the setup was that program, after finish computing, has to say, okay, I'm done, next program should start in. It wasn't working that well. You probably remember hung-up computers, blue screen of death. Yeah, that's how it was working. It was reliant on developer to exactly say to another project, I will be sleeping now, you can continue working. Wasn't a great idea. Next thing, Linux comes with help, and they implemented first scheduler based on the queue. It was single queue, then a circular queue. Algorithm was just picking next task in the list, giving some time to process, and then next one. All right. Currently, the two most popular solution is a multi-level feedback queue. It's used in Windows, Mac, and tree-based queue, also known as completed first scheduler, which is used in Linux. The first one, the multi-feedback queue, has a number of queues and tries to push down the processes which are more active up, and push down the processes which are less active, like background services, down. The idea is, like in completed first scheduler, to detect which processes are interactive. So they're basically waiting for user input, like a moving mouse pressing button. They sleep a lot, and give them shorter but more frequent executions, slices. And at the same time, services which are running in the background give them longer execution times but infrequent. So that's the basic idea about scheduling. However, we have another complexity which was called the non-uniform memory access. This is level 2, level 1, level 2, level 3 cache, and different access to different CPU cores to this level cache. It evolved a lot. In 2001, Linus Torvalds said, we don't need any more work on scheduling. And he was a little bit wrong, because between 2011 and February, there's about 780 commits just to this scheduling. It's a very complex thing. Scheduling by itself, it's called NP-hard problem, means there's no optimal solution. We have to either find a smart solution or brute force all of them. Well, brute forcing is not really an option, so you have to find some good solution. All right. What it has to do with scheduling? First people who work on the clusters, it was the term called meta computing, introduced in 87, first system Globus, another system Connor, HT Contour, which were basically deployed on university and trying to use the idle stations and do something with them. It evolved, and this was the base of the first scheduling, pretty much. First cluster scheduling. it evolved into something which is called monolithic scheduling, and this is when the operating system schedulers kick in. They try to use the same algorithms onto scheduling on the cluster of nodes like they use on the operating system. It's still pretty much used. Software like Kubernetes, simple Unix utility resource manager, or Fuxi, Alibaba Fuxi, which is quite interesting scheduler actually. It's still monolithic. What means monolithic? It means it has one machine which manages all the tasks. Oh, this machine can be replicated, but there's one decider who decides where the certain tasks go. This didn't scale that much. You can run about 5,000 machines nodes on this in this architecture. Alibaba Fuxi claims to have about 10,000 nodes. You cannot really verify that. However, this is probably the scalability limit. Next thing come Microsoft Dryad. What they said, all right, we have 20,000 nodes. Let's say 5,000 nodes for this particular task, 5,000 nodes for this particular task. Microsoft Dryad was used for Hotmail or providing the content. It was first time when they have to examine so much data, like, well, I won't say emails, like website traffic to present user advertisement. And that was the first system Dryad. However, it was not that efficient. As you can imagine, if you split machines, if you say exactly, we need 5 machines for that, 5 machines for that, some of them will be used, some of them won't be used. It's not a great utilization of the whole cluster. Therefore, they come with the two-level hierarchy. The very good example is Mesos. Next slides will explain that more graphically, so maybe just skim through it now. Another example of the two-level scheduling is Twitter. And then come shared state, Google Borg, Microsoft, Apollo. Maybe on the next presentation, we'll be also talking about big data frameworks. Big data frameworks are a little bit specific because the programming language is very intertwined with the scheduling mechanism. Like when you try to allocate this particular task to this particular node, when is this shard of the data you try to examine. We'll talk maybe next time. And there's another one, experimental, ongoing, decentralized, which in theory should scale above 100,000 nodes. All right. So where we are with these 3 architectures which are currently used. So a monolithic architecture, which means that all the scheduling happen on one machine. What's the importance of that? A cluster have a state. By cluster state, I mean which task on which is node, how many resources it consumes, and can we fit something else there. So that was the first monolithic scheduling. It keeps all the cluster state on the same machine, in memory usually, examines that, usually by some scoring algorithm. Kubernetes is the best example. And it provides allocation. However, once you have enough nodes, it's not efficient. Therefore, we have a two-level scheduling. When you have one state, which is kept in some sharded memory, which is also replicated for safety, and lots of different types of schedulers trying to claim those resources. A typical example would be, for example, Kafka and Spark competing for the same resources. The problem with this solution is they claim resources, they examine them, and then return them or claim them. And during the time when the resource is examined, it's locked. So that's the problem. That's what is called pessimistic concurrency. All right, so how to solve this problem? Google Borg, Google and Microsoft come with a solution. How about having multiple schedulers working on each of them has its own copy of the state. They allocate task and only in the way that the config the task is returned. This is optimistic locking. Only when the resources are committed to the particular task, then there might be collision or not. So that's the visualization of those 3 models. All right. However, this thing is a little bit more complex. Google Borg noticed something, and this might be a little bit familiar with people with Kubernetes. We specify the maximum that a given pod or job resource might take. We say this should scale up to 8 gigabytes of memory. However, most of the time application won't use this 8 gigabytes memory. Typical example is a daily mail when in the morning, every time opens the phone, tries to access phone in the morning, 9 a.m., the memory usage up to maybe 8 gigabytes. However, during the day, not that much. If there's news about Brexit, memory up again, and memory down. All right, so what do we do with this unclaimed memory? we know that those applications have to be able to scale up to 8 gigabytes. However, most of the time they don't. And this is something that Google calls production, non-production jobs. Microsoft calls them production and opportunistic jobs. Some jobs, some application needs to run continuously. Gmail needs to run continuously. However, if we have some big data job and we give them like 2 days to run, we don't need to run at this particular moment. So this is called opportunistic job. We start running it, and it finishes, it's fine. We put another one. However, if at this particular moment the production or continuous service requires the resources, we just kill this task. You can see. So this model allows Google current scheduler is called Borg. Reclaim resources. They claim they use about 80% of the claim memory. This is quite significant. In the next slide, I will show a little bit of this snapshot. This solution gives us a quite large computing cell to about 25,000 nodes, maybe even pushing 30. Gives a good allocation between the headroom balance. What is headroom? Our applications needs to be able to scale. Those opportunistic jobs also have a changing memory. Sometimes you can use like a half gigabyte, sometimes about 1 gigabyte. How much headroom do we have to scale? And this is how they solve it by moving averages. In this picture, we have a red line, which is the resources claimed by the production jobs. On top of that, we're giving a little bit of headroom, which is a moving average or step average here. This is the yellow. Yellow color, and above that we have a green color, which is the resources we can claim for the opportunistic jobs. How this looks like? Pretty much like this. As part of my research in University of Westminster, I was doing some Ph.D. there. I was analyzing the traces from 2011. Google in May 2011 published 1 month of the work traces of the computing cell of 12,500 machines. Those 12,000 machines are running on average about 140,000 jobs, so it's quite substantial. Like in the image before, the green is the resources allocated. Doesn't mean used, but means all the production jobs, this is how they require. You can see that Google engineers are underutilizing CPU, but they are using pretty much heavy memory. So this is something can be taken from that. People are not the best at saying how much it took CPU, but they are quite all right with judging how much memory it takes. The red bars is actually used by production jobs, but the blue bar is opportunistic jobs or non-pro jobs. So you can see, the production jobs always have a guarantee to be able to scale to the specified resources, so memory, CPU. However, because they're not running all the time at this maximum, we can still feed those opportunistic jobs there. On average, it does give us allocation about 60% of total cluster utilization of the CPU cores and about 80% of the memory. To compare that, this is a very substantial result. However, to compare that, Alibaba comes with something better. Come with the scheduler, which is utilizing about 97% of the memory and about 95% of CPU. They did the opposite. Instead of allocating jobs to resources, they're allocating resources to jobs. They have a queue of jobs, and they know which resources coming in, and they try to feed that into resources. They don't publish that much about the system. However, the statistics they publish are very impressive. Like I said, 95% utilization. However, the clusters are significantly smaller, about 5,000, maybe 10,000 machines. All right. How that all goes to Kubernetes? Kubernetes is not Borg. However, it's sharing DNA. They don't disclose what exactly is shared. From my reading, it comes mostly to this scoring function. Kubernetes works on, or most of the time, on Docker images. It has a structure, three-layer structure, when ingress service are providing proxy server and fault tolerance. Pod is the logical unit, containers is actually using application. They provide you namespaces with the secrets. They And exactly, and they have a scheduling. They have a single scheduler. Oh yeah, that's the architecture. They have a single scheduler, which is not continuously scanning the resources they have and try to match them to jobs. If someone was working on Kubernetes, we know that it's a declarative model. We declare what we need, and then the scheduler takes off the rest. As you can see, this is the monolithic architecture when the one scheduler is managing the whole cluster. And so this is the reason why sometimes the pods are pending for a while before it cannot find the node. Of course, it's more complex. At least in our installation in government, we have auto scaling. When normally we work on a certain number of nodes, if needed, we can request more, which is more expensive. All of this is working on AWS. All right, so this is pretty much the architecture of Kubernetes. To make a quick summary of that, because I guess there was a lot of information. Operating system schedulers is a non-stop balance between the interactive processes and background services. Interactive processes supposed to sleep more, supposed to be run more frequently, but on shorter time slices. Background services supposed to run on the longer time slices, but less frequently. It's also low complexity algorithms, usually ON, O1, even sometimes O1. The completely fresh scheduler has O1 complexity because we don't have time to allocate it. Cluster schedulers are roughly split between monolithic architecture, which is like a Slurm, Kubernetes, Fuxi, and between concurrent schedulings, which of them can be separated into three groups. Like I don't think it's no longer used Microsoft Dryad. However, they're very much used now. Two-level scheduler like a Mesos, and the shared state scheduler. As far as I know, the only two shared state schedulers are Microsoft Apollo and Google Borg. Google Borg is way more published. Well, I guess the Google guys like to talk about their work. So that's the current state of the scheduling on the clusters. All right. This, what I said, is much more. There's much more details about this. I prepare the link when you can read more details, and also providing a bonus when you can use that tooling image. One of the things that Kubernetes doesn't provide is the easy maintenance. And therefore, we prepared a simple node, simple pod, simple image. You can use it. It's open source. If you need to add any more tools, just let us know. We just add them. And there's also another problem in Kubernetes that pods are not persistent. So how to save data? We also provide the example of the persistent volume claim. So that's about the questions.